let's begin.
So, these are the remaining examples from last time. Gonna go through them sort of in the same vein. So, start out by graphing and then try to figure out how the limit behaves here. So, how does this graph look? Yeah?
Straight line.
What straight line?
The straight line is a point at 0, 2.
Okay, passes through 2 on the y-axis, and how does it behave?
Increases.
Okay, but what's the slope?
Oh, 1/1. So it's like
How do you
you go up
get
one
that?
and then you go to the right one.
How did you get that?
So you simplify the top. X was 2 times x minus 2.
So we can simplify here. X plus 2 times x minus 2 over x minus 2.
Then you cancel.
That cancels, so this behaves like x plus 2. So is that exactly x plus 2? There's no difference between x plus 2 and this guy? Can you do everything with this guy that you can do with x plus 2? What's the issue? Yeah?
The denominator can't be equal to 0, so you can't have x equal to positive 2.
Right, so, and by the way, that stays. X cannot be 2. So that's something that students often forget. Simplifying doesn't fix your domain. So you simplify, but it's still the case that if 2 didn't work in the beginning, it's not going to work after you finish simplifying. Right? So you're not allowed to plug in 2. What does that mean for our picture? Yeah?
There's like a hole in the graph.
There's a hole. So at 2 actually cannot work. So there is a hole. And that is a technical term, by the way, it's a hole. Like definition, like in a textbook, a hole. Right, so when a function can't work at a isolated point, we call that a hole. So there's a hole at 2, but otherwise, for every other point, this function is going to behave just like x plus 2, because as long as we're not dividing by 0, it's just a fraction that we can reduce, we can simplify that. And so that's our picture. Now let's play the same game. As I'm inching closer and closer and closer to 2, means I'm on the graph inching closer and closer and closer to some point where the y value is going to be something over here. And the same thing from this side, if I'm inching closer and closer and closer to 2, and on this side of the graph, inching down to a location where those guys seem to be matching up. The y values seem to be zooming in on something. What is that thing that they appear to be zooming in on? What do you think this y value would be for that location? 4. It behaves like x plus 2. So when your x is getting close to 2, it's going to behave like it's getting close to 4. Now, it will never actually make it to 4, but limits don't care. Limits do not care about being at a point. They just care about what happens as you get close to the point. So I would be able to say the limit as x approaches 2 of this guy is 4. Now, the function itself never actually outputs the value 4, but the limit doesn't care. Okay, so that's the first one. That's what the picture would look like, and that's how the limit would behave. What about this picture? What would this look like? does that one look like? Yeah?
Is there a horizontal line on one?
Just like this?
Mm,
Yeah?
Up until you get to the X value of 1 or something.
And what happens at 1? So is that up until I get to 1? What happens at the 1? Yeah?
It
Yeah.
stops and there's an open hole.
In the circle, there's a hole there. Okay, and then? Yeah?
For the x is greater than or equal to 1 on the second thing, I know, do you do like a closed circle and then draw a line going to the right?
Well, where would be the closed circle? If x is equal to 1, what is the function? What's the value? Yeah?
Maybe put a closed circle on, like the 1 on the x-axis, like right there. And then have that, yeah.
Okay, and then what? What's the other side gonna look like over here? Curved line up, it's like a parabola.
Yeah.
So that is the picture. Remember how you can draw piecewise functions? If it helps you to visualize, you just draw them one at a time. So you have y equals 1, that's just that line there. But you realize that that only works for less than 1, so there's an open circle here, and you ignore everybody greater than 1. If you have that y equals x minus 1 squared, well, that's just like a quadratic, shifted 1 unit over. And of course, if you want to be greater than or equal to 1, you care about this side and you ignore that side. And then you kind of just draw both pictures on one graph at a time. So this point here, when they said less than 1 versus greater than 1, they're basically telling you there's this invisible barrier here that's going through 1, and on the left side of that barrier, it's doing one thing versus on the right side. So you draw the, this is a piecewise function it's called, and you graph them in pieces, right? Piece by piece. Right? So that's what the picture looks like. So if you play the same game here, so I'm inching closer and closer to 1 from this side, then on the graph I'm here, inching closer and closer to 1, then coming over here, my y values are approaching 0. I'm inching closer and closer to 1 from the left side, then on the left side I'm over here, inching closer and closer to 1, and the y values are approaching 1. And so, that being said, what is the limit as x approaches 1 of our function? Yeah?
It doesn't exist.
Does not exist. Does not exist would be the answer here. And called some students earlier in my morning class. This is still morning class as well, but whatever. Too early. Seeing that this point filled in, some people were tempted to say the answer is 0. But what you need to remember about limits don't care at all about who's filled in. You do not care about being at the point at all. You care about what's happening as you get close to the point. Now, as you're getting close to the point, your y value disagrees. There's disagreement and ambiguity between where the y value is going. From one side it's coming to a 1, from the other side it's going to a 0. Disagreement. That violates our definition. Limit does not exist. Because your y value, there's no unique y value that we're approaching as your x is approaching 1. But some of you might feel a little bit unsatisfied by that, and I would know how you feel, because if you think about what a limit is supposed to be doing, of course it's about examining a function around a point. Now at that point something crazy might be happening, we don't know how to deal with it, or it's very complicated. But the limit doesn't care about the point itself, it just tries to figure out how the function is behaving in a neighborhood of the point. When you're very close in the general vicinity of the point, what's going on? What's happening to our y value? And so while here, by our definition, technically this limit does not exist, on the other hand, no pun intended, we can actually know how our function is behaving on either side. Like I know exactly what's going on, it's just that it doesn't fit this definition that I arbitrarily came up with earlier. And so this leads us to, sorry, wait here, this example leads to another notion where sometimes our limit can not exist, but we can examine the functions on one hand or the other, one side at a time. It's called one-sided limits. Limits. So here's how, because notice I can talk about from one side or the other, I can talk about from the left or the right, and I know exactly what's going on. So the notation is the following. I can have limit as x approaches a of f of x, but I put a little plus sign here in the upper right corner, kind of like a superscript here. Whenever you see that notation, that is the limit as x approaches a from the right of f of x. And so I'm coming from the right. Right? And I can indicate that by putting a little plus sign. So from the right means I'm a plus a little bit, right? So I'm 1 plus a little bit, meaning I'm over here, and I'm getting closer and closer to 1 from that side. After being, so I'm slightly bigger than 1, right? So this means I'm slightly bigger than 1. Sort that. For a. So x is slightly larger than a. And so, okay. So I can talk about the right side limit, the one-sided limit. We also have a f of x with a little minus sign, so the top, there's a negative in the upper right-hand corner. Right? That doesn't change the sign of anything, it's purely a directional notation. This is the limit as we're coming from the left. So here we're slightly smaller than a approaching here. So I'm a minus a little bit, right? So I'm 1 minus a little bit, means I'm over here, and I'm getting closer and closer to it from that side. Right? So that's called a limit from the left. So, in the above, which, I mean, it's to the right here, but for you guys it might be above in your notes. The limit, I can talk about limit as x approaches 1 from the right of our function, and I can talk about the limit as x approaching 1 from the left of our function. What would this one be? Yeah? This?
Or, oh yeah,
limit as I approach 1 from the right, 0. 1. So one side at a time, I can fully determine what the y value is doing. But putting them together, the 1 and the 0 disagree. And so overall, the limit does not exist. That leads us to, I think, another definition, which is probably a better word to use for this than definition. Convention? No, not really. The limit as x approaches a of f of x only exists if both one-sided limits exist, so the limit as you approach a from the right of f of x, and the limit as you approach a from the left of f of x exists. And they're equal. Then your limit here is the common value. Now, once these two disagree, your limit does not exist. And it's also possible for one or the other here to not exist. Either one-sided limit might not exist as well in its own right. So if either one of these don't exist, or if they both exist but they give you different answers, then the overall limit does not exist itself. So once the limit exists, all three of these will give you the same value, and that's one we can actually check. So that's the notion of a one-sided limit. At this point, I want to make some more remarks. So one, f of x need not be defined at x equals a for the limit to exist. So again, to reiterate, we do not care about where we're filled in, is the point there, is it on our function, the limit does not care. We care about what is happening to the y value as we inch closer to the point. So it cares about what the y value gets close to, and a phrase you'll see in your text, or I might even say it, arbitrarily close to as x gets close, arbitrarily close to a. And by the way, what does arbitrarily close mean? Essentially, arbitrarily close means as close as you want. Means you can get closer than any given positive distance. So the answer to the question, can we get closer, is always yes. If that's the case, you say we can get arbitrarily close. So, for example, here you can have a function. At 1, it doesn't exist, but it looks like that, meaning I can get as close as I want to 1, I just can't be at 1 itself. So here we can get arbitrarily close. Compare this to something that behaves like this. Here's a 1, here's my point. and there's like a gap here. Say you have a picture like that. Say this is at a half. This is at 2. Right? Now someone asks you, can we get to within a quarter unit of 1? Your answer would be no. So if I'm here and I say, can we get closer? No. If the answer is no, it means you cannot get arbitrarily close. Right? So it means that I can't get to within any positive distance of 1 that I feel like. Right? The closest I can get is to within a half a unit. But if I want to get to within a quarter of a unit, can't work. There's a gap. There's a gulf here that I can't jump. So we can't get arbitrarily close. But let me emphasize the not. We cannot get arbitrarily close. So here, by default, the limit as x approaches 1 of your function will not exist. Right? Now, yes, the function is filled in, the point is there, I can see it, it exists, the function works, but I can't actually get close to that point. Right? So there's no way to get as close as I want to that point without ever actually being that point. Right? That's very important for the limit. So you want to be able to inch close to something. You don't necessarily care about being there, but you want to get as close as you want to there. Right? And that's what the limit cares. What happens if I try to inch as close as I want without actually getting there? Right? Tell me what the y value is doing as I do that, and that's the limit. Another comment here. So if, now sometimes something magical happens, and the limit as you approach the point is actually equal to the value of the function at that point. Right? So that can be like, okay, here I'm approaching 1, I can get arbitrarily close, and at the same time it's actually filled in to the thing I'm getting arbitrarily close to. Now whenever that happens, we say f is continuous. At x equals a, right? So if I could get close to that point, the limit exists, and it's actually equal to what the function is, we say the function is continuous. And we'll talk more about that soon, but that's just a phrase I want to use a little bit later, so I'm going to tell you guys what that is. Another thing I want to mention. In the limit as x approaches a of f of x equals L, if your L is equal to plus or minus infinity, we call the limit an infinite limit. So for example, the limit as x approaches 0 of 1 over x squared, we saw that last time was infinity. That is called an infinite limit. Right? The y value goes off to infinity, it's an infinite limit. If the a value is plus or minus infinity, so the x value that I'm looking at is just going off to the right or to the left, we call the limit limit at infinity. Example, the limit as x approaches infinity of 1 over x equals 0 is a limit at infinity, right? We're taking the limit at the value infinity. The y value goes to 0, but we're taking it at the x value infinity. So notice a limit can be both. So if I look at, say, the limit as x approaches infinity of x squared, that will actually give me infinity as the answer, and that is an infinite limit at infinity. Those are just some terminologies that we can use here. At the moment, I think that's all the remarks I want to make. But I want to talk about something that's very important. We're going to talk now about computing limits. So now we were finding limits earlier in last class, but kind of in an intuitive way, kind of clumsily, like looking at the graph and inching closer. How can we do that more efficiently? How can we calculate something? Perhaps without even drawing the graphs. Right, so I'm going to give you the strategy for actually doing this. Because finding limits is something you need to be good at in calculus, and on the next quiz, I'm definitely going to ask you a problem where I'm just going to give you a bunch of limits. I'm going to say, find the limits. You're going to have to just compute them. So I'm not going to give you any hints or what to do. You're just going to have to realize how you're going to approach it. You're going to approach it that way, and you're going to come up with the right answer. Okay? And so if I give you a random limit when faced with some limit, right? So this is some random limit I'm giving you. You don't know what it looks like. It might even look very scary, but we're not going to be scared because I'm going to tell you exactly how to deal with any of these guys. Faced with some random limit, there's a set of steps that you want to go through. Step 1, always the first thing you try to do. Try to plug in x equals a. Try to plug in the number. Right? Now, in this class, functions are nice, so nice to the point where if we can actually plug in the number, then it means that we can't actually get arbitrarily close to the number because we're technically going to always be looking at continuous functions here. Right? If f is continuous, then you can find the limit by plugging in the value. Now we're mostly going to be dealing with continuous functions, polynomials, trig functions. We're not doing trig, but they're also continuous. Radicals, rational functions, exponentials, logarithms. These guys are all continuous on their domain. Meaning, if you're at the point, if you're in the situation where you can plug in a point, it also means you can arbitrarily get close to that point. All our functions will have that kind of property to them. Even though that's not general, but in Calc 1, that's always going to be the case. So if you can plug in the number, try to plug in the number. So for example, our very first example, we're asking you to figure out what is the limit as x approaches 1 of the function 3 minus x. And we drew the graph and all that. You could have actually just as easily plugged in 1. Answers 2. 3 minus x is a very nice graph. Y equals 3 minus x, that's a line, it's a polynomial. It's continuous everywhere. There's no gaps, there's no jumps, there's none of that spacing that I have to worry about. I can get as close to 1 as I want, and the y value is going to behave very predictably and in unison from either side. I can figure out what the limit is by just plugging in the value. The limit is actually 2. And you'll realize that that's the answer that we got, actually, the first time. Right? So that's step 1. It's an easy step, and it's always the first thing you try to do. You always try to plug in the number first. Always step 1. So sometimes step 1 doesn't work, and we need step 2. So let's say you want to plug in the number, but you can't plug in the number for some reason, because you divide by 0, or you have a negative under a radical or something like that. So step 2, you can't actually plug in. What you do is you try to simplify so that you can plug in. So here's an example. The first one we started with today is an example. So you had x squared minus 4 over x minus 2. So Step 1, I'm gonna try to plug in 2, can't plug in 2 because I divide by 0. If I plug in 2 and divide by 0, Jhevon's gonna kill me, so I'm not gonna do that. Can't do step 1. But, next thing I'm gonna do, can I simplify this? Then I start to think, well, yeah, that's the difference of squares. You'll recognize because we're great at algebra. That's gonna cancel here. Then I have the limit as x approaches 2 of x plus 2. So as long as we're not at 2, this behaves like x plus 2. The limit doesn't care about being at 2 either way. So at this point though, it's something nice that I can actually plug in. So I'm going to plug in the 2. And the answer is 4. One thing I wanted to note here is that we keep writing the limit sign until we actually take the limit. So notice here that I was writing this limit sign here. I'm writing the limit sign here. Right? So while I'm simplifying, while I'm breaking it down, I keep writing LIN, keep writing the limit part, right? Because I didn't actually take the limit yet. Once I get to a point where I can take the limit, I can either plug in the number or I can realize that it does not exist. At that point, I drop the limit sign. So, no limit sign. Because now I'm at the plugging in stage. I can actually evaluate the limit or take the limit, right? So keep writing LIM until I get to a point where okay, I know how to just compute this now. And then you drop the limit sign and that's your answer. So that's going to be 4. So your y value is getting close to 4 as your x value is getting close to 2. How close? Arbitrarily close as you want. So that's the next thing you're going to do. Now, of course, sometimes that doesn't work, which leads us to step 3. Now, step 3, we're kind of going to have to put a pin on it, use a special technique, which I didn't tell you about any special techniques yet, but I will. We'll come back to this. Kind of hyping it up for no reason, because I think in this class I won't give you guys one of them. Because a lot of the other ones, they really come in handy with trig functions and stuff where we're not really going to do anything with trig functions. So there's probably like 1, maybe 2 special techniques. But sometimes you're looking at a formula that has a certain pattern that we know we can take advantage of, we know how to deal with it. And so we would use that special technique. I'm going to show you at least one of them. So step 4. Let's skip over that, or step 5. These are kind of interchangeable, it just depends on what you're looking at. But, okay, special technique doesn't work. You can't plug in, you can't simplify. Here's one thing you can do. You can use the graph or the table of values. So, example. Limit as x approaches 0 of 1 over x squared. Okay, step 1, try to plug in 0. Can't plug in 0. Do that, Jhevon kills me. Okay. Step 2, try to simplify so I can plug in 0. Can't do that either. How am I going to cancel those x's? Top is a 1. Nothing I can do to simplify this. That's as simple as it gets. Okay, so can't plug in the number, can't simplify to plug in the number. What do I do now? Well, one option is, if it's easy to graph, you know the graph, or you can pretty much figure out the graph without too much trouble, draw the graph. Right? You know the graph of this looks like that. I can see from the right side it's going up to infinity, from the left side it's going up to infinity. Hey, the limit equals infinity. So that's one way to just look at the graph, watch the behavior from the picture. Pretty much the same that we've been doing last class and the beginning of this class. Use the picture to tell you. Now, every now and then, you don't know what the picture would look like, you don't know what the graph looks like, or you don't want to have to actually go through the trouble of drawing the graph. another option you have is to use a table of values. So, again, the same example, what I could do is I could just come up with a table of values. Now, how long this table is almost arbitrary. You just want to go long enough for you to actually talk about, see some sort of pattern happening. So let's say you care about 0, but you don't know what's happening at 0. Okay? So you're going to try to figure out what's happening at 0. So you inch closer and closer to 0. How close? Arbitrarily close. So you don't want something far away like 1. You want to be very close, like say 0.1, 0.01, 0.0001, right? You're inching closer and closer to 0. Super close, you get very, very close, like a few decimal points off. Okay? And then you kind of examine what does the output 1 over x squared do? Well, 0.1 is 1 over 10. You take 1 over 10, you square it, and then you take the reciprocal. You would get 100 here. Do the same here, you'll get, I think, 10,000. Do it here, you'll get like 1,000,000. Now what you're trying to do is find a pattern. Now you should see what the pattern is doing here. These just keep getting bigger and bigger. They're going off to plus infinity as I move towards 0. You can actually do the same thing going the other way. Minus 0, 1. And in this situation, what's going to happen is the square is going to get rid of the negative sign, so you'll actually get pretty much the same numbers. And of course, you see that as you move towards 0, the pattern keeps getting bigger and bigger and bigger. So that's also going out to infinity. So what do I think the answer is going to be here? Well, it looks like infinity is the candidate that we want. Every now and then you'll see these numbers start to settle somewhere. And that's the table of values. This can be expressed as there's another way to kind of do this idea, but you kind of do it in the formula itself. So you're looking at the limit as x approaches 0 of 1 over x squared. What you can say is the top is 1, I can't really do anything to that. And the denominator is getting close to 0, but it's not quite 0. In fact, it's getting close to 0, but it's being squared, so I can say it's 0 with a slight positive charge. I put a little plus sign. And you have to put that little plus sign, because if you don't, Jhevon's going to kill you. Can't divide by 0. So, put right in this little plus sign kind of indicates that I'm not dividing by 0. I know I can't do it, but this is slightly positive. But close to 0. So it's not 0, I'm getting close to 0, but I'm slightly positive, right? So the x squared is going to be positive. Now, if you have a fraction where the numerator is not approaching 0, because 0 over 0 is a whole other ballgame. If the numerator is not approaching 0, but your denominator is approaching 0, it's going to blow up. Because if you have a fraction where the denominator keeps getting smaller and smaller, keep, change, flip, you take the reciprocal, it gives you a bigger number. So that means it's going to go off to infinity, and you kind of have to watch the sign. So positive, so it goes off to positive infinity. Let me show you a slightly more complicated example where you can apply this idea so you can see how it works. Let's say on a test or a quiz or whatever, I ask you, compute this limit. Right? This kind of reminds you of the guy we started class with. Okay. So you see that, step 1. Try to plug in the number. Can't plug in the number. Right? Step 2. Can I simplify to plug in the number? So that would be the next thing I'm trying. Okay, let's try to simplify this bad boy. That is difference of 2 squares. So damn it, nothing cancels. Step 2 doesn't work. Step 3, special technique, let's skip over that. Step 4, don't really feel like graphing that, and I also don't want to plug in the table of values because Jhevon says we can't use calculators, so that's going to take forever. One way we can kind of use, one thing we can kind of do is this idea. Okay, so there's no way I can simplify to get out of a potential division by 0. So now I'm just going to start to see what are the charges here. The x minus 2 factor, if my x gets close to 1, then x minus 2 is going to get very close to minus 1. That's going to get very close to 3. Now the denominator, let me put a little charge here. Now let's say I'm approaching 1 from the right, so you can kind of see what I'm talking about. In the other case, it would not exist. If you're approaching 1 from the right, it means your x is slightly bigger than 1, so your x minus 1, this is something slightly bigger than 1, so if I subtract 1, I'm going to get something slightly positive. So it's getting close to 0, but it's with a positive charge. And so what you can say here is that, all right, the numerator is not 0. The denominator getting close to 0. Positive charge. So this thing, you can't stop it as well. So you can't even simplify it because you can't. You tried step 2, it doesn't work out. So this thing is trying to divide by 0 and there's no way for you to stop it. The numerator is not 0 though. What happens is that the fraction is going to blow up. It's going to become infinite. Now, once you know that it's going to be infinite, you have 2 options, positive infinity or negative infinity. How do you pick? Well, now you observe the signs that are going on. Notice in the numerator you would have a negative sign, while in the denominator it'll be slightly positive. So negative infinity is going to be the answer. Now, of course, if you had the limit as x approaches 1 of this guy, you'll notice that if you look at things separately, the limit as you approach 1 from the right versus the limit as you approach 1 from the left, this guy is going to give you negative infinity, as we discovered. This guy, if your x is a little smaller than 1, notice that this guy, x minus 1, would be negative, so it would be 0 to a slight negative charge. This guy is going to be minus 1, 3, with 0 with a slight negative charge. So it's negative divided negative. This guy is going to give you positive infinity. So overall, the limit does not exist. Right? One side at a time, they disagree. Another way you can express it, but that all kinds of comes into the plug in values and see what's going on kind of method. And the last strategy, so this would be step 5 or step 4, depending on who you see first. Use your knowledge, yes, you have knowledge of the behavior of functions. Now some of these behavior I already told you about, so let me just expand that list a little bit. Log to the base a. We know that logarithms are much smaller than polynomials, which are much smaller than exponentials, which are much smaller than factorial. That's called a factorial. We're pretty much never going to see that again in this class, but you'll see it in Calc 2 if you have to take it, or something like a probability or statistics class, which is smaller than, say, something like that. Okay. And this is as x goes off to infinity. So remember what this means. guys on the right are much bigger than guys on the left as x goes off to infinity, in the sense that guys on the left compared to guys on the right, guys on the left are like very small, they might as well be zero kind of thing. So one way in which you can actually use that, let's say I have this limit, let's say x to the fifth minus x to the fourth over, see, something like that, right? So I look at that, can't plug in infinity, infinity is not a number to plug in. Can't simplify, don't want to do the graph or a table of values, that's going to take forever. And I don't know about the charges idea, how's that going to work? Like both, that's going to have a positive charge on top, negative charge on bottom, but I don't really know any more than that. However, by looking at the functions that show up, notice that in the numerator I only have polynomials. In the denominator, I have an exponential. Exponentials are bigger than polynomials, like really, really bigger once we're going off to infinity. What you'll notice is that the denominator is going to get really big, and the numerator, relatively speaking, is going to be very small. So this is going to look like small over, this is huge, right? That's the kind of fraction, right? Now, if you have a fraction where the denominator is huge and the numerator is small, what does that fraction behave like? What does that go to? Yeah?
You approach 0.
Approach is 0. So I can just look at that, answer is 0, right? But I really went through a bunch of steps in my head, but it's clearly 0. It's a polynomial over an exponential, and they're going off to infinity. Exponential wins. Denominator overwhelms the numerator, that's going off to 0. As far as showing work is concerned here, you could say something like, it's bottom heavy. It's bottom heavy, the bottom is really heavier than the top. It's going to go to 0. That's how fractions work. Right? When the denominator gets huge, the fraction gets small. And so just by me knowing about functions, I can look at that and know what the limit is. So kind of end there. Those are the main strategies. Of course, we'll expand on step 3 with some techniques next time. But for now, that's it. Next time we'll go through a bunch more examples where we're using these strategies. So we'll do that on Friday.